Dear students, now we are going to discuss about DeMorgan's theorems with its proof in detail.
A famous mathematician De Morgan derived the two most important theorems of Boolean algebra. These theorems are called as De Morgan's theorem. These are the powerful tools used in digital system design. Let's discuss De Morgan's first theorem in detail. The first theorem states that the complement of the sum of all the terms is equal to the product of the complement of each term. That is given like this. Here we consider only two elements A and B. So A plus B the whole bar is equal to A bar into B bar. Here bar represents the complement. So first theorem states that the complement of the sum of the terms is equal to the product of the complements of each term. So we are going to express this as a diagrammatic representation like this. So here this left hand side A plus B the whole bar can be represented like this. A and B are the inputs given to this OR gate. We can get A plus B. This A plus B is the input to this NOT gate. Then we can get A plus B the whole bar. That is equal to the right hand side can be represented like this. Inputs are A and B. Here this bubble, correct, this bubble symbol represents the inverting operation. That is the complement of the input A. So after this bubble, the value is A bar. Here it is B bar. This is the AND gate. It is going to give the result as A bar dot B bar. So after this symbolic representation, we are going to prove this. That is A plus B the whole bar is equal to A bar dot B bar. For that, we are going to use truth table. Here A and B, these are the inputs. So 0, 0, 0, 1, 1, 0, 1, 1. These are the combinations of inputs. So A plus B, 0 plus 0, 0, 0 plus 1, 1, 1 plus 0, 1, 1 plus 1 is equal to 1. We are going to take the inverting operation, that is the NOT gate. A plus B the whole bar. So 0 becomes 1, 1 becomes 0. So this is the output for this left hand side, 1, 0, 0, 0. Correct. So here consider the right hand side. A, B are the inputs. So these are the combinations. And here A bar and B bar. So here 0, 0 becomes 1, 1. 0, 1 becomes what? 1, 0. 1, 0 become 0, 1. 1, 1 become 0, 0. Here A bar dot B bar. That is product of these two elements. Here 1 into 1, 1. 1 in 0, 0. 0, 1, 0. 0 in 0, 0. So now we can say this is the output of the right hand side. So now we can compare these two. Both the outputs are equal. So the theorem is proved by using the truth table. Next we are going to prove the De Morgan's first theorem using Boolean algebra. From this Boolean algebra we know that A plus A bar is equal to 1. Multiplication of A and A bar is equal to 0. The same statements can be written like this. A plus B plus A plus B the whole bar is equal to 1. Sum of A plus B and A plus B the whole bar is equal to 1. The product of A plus B and A plus B the whole bar is equal to 0. In order to prove De Morgan's first theorem, we are going to take this statement A plus B plus A plus B the whole bar. We need to prove this first statement. Okay. So here we can write this a plus b as such. This a plus b the whole bar can be written as a bar dot b bar from this DeMorgan's first theorem, because we are going to prove DeMorgan's first theorem. Instead of this a plus b the whole bar, a bar dot b bar is used. So we are going to make sure that the resultant value should be 1. So a plus b the whole bar is equal to a bar dot b bar here. So in the next step, using the postulates, this can be multiplied like this. A plus b plus a dot b can be written as a plus b plus a bar dot a plus b plus b bar. So we know that a plus a bar is always 1. These are the postulates. That is fundamental laws of Boolean algebra. We have already discussed in the previous videos, right? So a plus a bar is equal to 1. Likewise, b plus b bar is equal to 1. So we can write here 1 plus b dot a plus 1 or 1 plus a. Correct? So here 1 plus any element. It can be A, B, C, whatever it may be. 1 plus any element is equal to 1. So here this resultant 1 plus B is equal to 1. 1 plus A is equal to 1. 1 dot 1 is equal to 1. So instead of this A plus B the whole bar, we have used A bar dot B bar. With that, we have obtained the value 1. So DeMorgan's first theorem is proved. So likewise, we can prove this second statement also. For this second statement, take this left hand side. So a plus b dot a plus b the whole bar. Correct. This is the second expression. So here again, by using DeMorgan's first theorem, this value can be replaced as a bar dot b bar. So a plus b dot a bar dot b bar. That can be written like this. A dot this. Okay. A dot a bar b bar. Then plus b dot a bar dot b bar. So here a into a bar is equal to what? It is always 0. Not only a into a bar, any value, x, consider any value. Any element multiplied with its own complement produces 0. Correct. So here this a into a bar is 0. B into b bar is equal to 0. So the resultant value is 0. So we have proved the DeMorgan's first theorem. A plus b the whole bar is equal to a bar dot b bar. DeMorgan's second theorem states that the complement of the product of all terms is equal to the sum of complements of each term. The statement can be expressed as a dot b the whole bar is equal to a bar plus b bar. The product becomes sum. This expression can be represented diagrammatically as a, b are the inputs. Consider the left hand side here. A and b are the inputs. Here it is the NAND gate. NAND gate means what here? It is nothing but combination of NOT and AND. The output of the NAND gate is A dot B the whole bar. Okay. So this is the left hand side. That is equal to the right hand side can be represented like this. The inputs are A and B. Here the bubble represents the inverting operation. So we can get A bar and B bar after this bubble. Here it is the OR gate. So we are going to add these two input values as A bar plus B bar. So this is the diagrammatic representation of DeMorgan's second theorem. The second theorem can be proven by using the truth table. So for this left hand side, we can take this truth table A, B. These are the inputs. Combinations are 0, 0, 0, 1, 1, 0, 1, 1. A dot B answer is what? It is normal multiplication. We can get 1 when both the inputs are high. Here the actual output is A dot B the whole bar. So here 0 becomes 1, 0 becomes 1, 0 becomes 1, 1 becomes 0. So this is the actual output of the NAND gate. Consider the right hand side. Here again two inputs A and B. We are obtaining the complementing operation using inverter. So 0 0 becomes 1 1, 0 1 become 1 0, 1 0 become 0 1, here 0 0. So we are going to add these two value. Correct. Add these two values. We can get 1 plus 1 1, 1 plus 0 1, 0 plus 1 1, 0 plus 0 is equal to 0. This is the output of the right hand side. So both the outputs are equal. So by using this truth table, we have proven the DeMorgan's second theorem. So next we are going to prove DeMorgan's second theorem using Boolean algebra. Here Boolean algebra, a plus a bar is equal to 1. A dot a bar is equal to 0. Here we can consider a as a dot b. So the statement can be written as a dot b plus a dot b the whole bar is equal to 1. Likewise ab dot a dot b the whole bar is equal to 0. We are going to prove these two statements by using DeMorgan's second theorem. So consider the first statement a dot b plus a dot b the whole bar. Here we can write this a dot b the whole bar as a bar plus b bar by using DeMorgan's second theorem. Correct. So this a dot b the whole bar is nothing but a bar plus b bar. So we can write this as like this a dot b plus a bar plus b bar. So we can state the statement like this a bar plus b bar plus a dot. Correct. Next a bar plus b bar plus b. So next we know that a plus a bar is equal to 1 always. Likewise b plus b bar is equal to 1 always. So 1 plus b bar, here it is 1 plus a bar. So here anything, any element plus 1 is equal to what? This can be a bar, this can be b bar or whatever it may be. 1 plus any element is always 1. This is what the Boolean law. So here we can say this value as 1, this value as 1. So 1 into 1 is equal to 1. Then the statement is proved. So next come to that next statement. A dot b dot a b the whole bar. Here we can replace this ab the whole bar as a bar plus b bar using second theorem. So we can write like this and then multiply inside we can get ab a bar plus ab b bar. So we know that a bar is equal to 0. So this term becomes 0, this term becomes 0. Finally we can get the answer 0. So since these two statements are true, the DeMorgan's second theorem is also proved.